check the time. So it's the hour. Maybe first a word on me. So my name is Ben. I started doing this line of work a couple of years ago. Started on Ethereum in 2016, then I cut 2 years later. And then we started this company, OST, 2 years ago almost, 2017. Because we saw the blockchain hype happening and I was building on Ethereum, and I realized that if we can't move the infrastructure forward, a lot of these things will potentially become winter, and I did not care to create or destroy my new career with a winter. So I really try to address sort of the question, how do we make Ethereum 1x work and get to actual use cases? And so since we've worked on what we now call Mosaic, and this is a short presentation on Mosaic 1, which would be the first full dApp with open validators on Ethereum 1x, but I'll get into that throughout the talk. Let me see how this works. So the outline is very simple. I want to say a few words about Ethereum 1x, and then I want to say something about Mosaic. The numbers are a little bit outdated, but they haven't significantly changed. So in April last year, I checked Etherscan, and roughly we do 100,000 one gas operations, so additions per second on Ethereum right now. And I'm comparing apples with oranges, so all the critical spirits, just bear with me on this slide. It can be very critical later. But for every operation we do in the EVM, we still have to also execute ETH hash, and that ran at some 150 terahertz. So if you would say 6,000 operations per hash, you roughly come to 10 to the 17 operations, which isn't bad because that's world computer performance scale, but we're wasting a lot of that, right? There's 12 orders of magnitude between the number of operations we execute in the EVM and the number of cycles or operations we do to get proof of work. And so if you just take a very standard thermodynamic argument, you divide the useful part by all the stuff done, which is still 10 to the 17, you have an efficiency of 0. I mean, approximately 0. And so the question is, why do we care to run a machine at near 0 efficiency? Apparently we spend millions of dollars a day to keep this running because we mint ETH and it has a stable value. So we pay off electricity bills. Why do we pay this cost? Why do we run the most, there's Bitcoin as well, but why do we run the most inefficient machine I can ever think of and keep running it? And my argument is that it uniquely builds a collective state. It solves a problem that we weren't able to solve before. And I think that's why it's worth trying to improve the efficiency of it. Because it allows to connect otherwise unconnected, isolated intelligence, whether that's people, companies, edge devices. But right now we're in a very, very early age of this machine, of course. And so then the question I asked, who is addressing the scalability for the existing ecosystem? There were a lot of projects building this. And maybe this is my cynical slide. But Polkadot, Cosmos, great projects, but they're building a new ecosystem. Ethereum 2.0, yes, but we've just stabilized phase 0, and it will take a while before we get to feature completion of what we have today. And then the layer 2 solutions always scale one dApp at a time, not Ethereum 1x itself. They don't aim to even extend the interface. And a lot of them even restrict what's possible back to UTXO transfers, to just token transfers. So that's why Mosaic is a dApp to scale Ethereum 1x itself. And so my moonshot challenge, that we're posing ourselves, but happy to invite anyone to it. Can we make Ethereum 1x 100,000 times more powerful, more efficient? It will still be near 0 efficiency, I acknowledge that, but it's already a lot more power that we'd get. So that's the first part, my short introduction of why I think this is worth trying. And then to introduce Mosaic itself, it's really often said, and it's partially a good analogy, but I think it's not a very helpful analogy. Like blockchain is in the time of 1990s, where the internet was then. It wasn't very useful, blah, blah, blah. Everyone like goes with this analogy. I think it's not very helpful because it doesn't tell me how to build a better blockchain. Whereas if you think about the 1990s, we had an Intel Pentium processor and it ran at 60 megahertz. And then 6 years later, we had 10x that and we had a Pentium 3, which ran at 600 megahertz. But 1999, I bring this up because it's also the introduction of the first GPU. And the GPU was a card that you plugged into your existing computer to make it do more computations. Because it took another 7 years before the first like desktop dual core processor came around. It wasn't an easy task. It was also a different task. So by 2006, NVIDIA was at its like GeForce 8 series. So this is just a historical fact. I went over to Wikipedia earlier today. And so my claim is, or my position is that, I mean, we'll all agree that like Ethereum 1x right now is sort of the Pentium and we're being generous, right? Like we can't do that much on Ethereum, so it's a single core. It's really like almost an embedded device. It's very similar like constraints you'd have to solve for. And of course, like we're not 2006 or the 1990s, so our version of like a dual or a multi-core processor will be one that runs with 1,000 shards. We won't go to 2 cores, we'll go to 1,000 shards. But it's a hard problem. And the question is, can we not build a GPU in the meantime that gives us 100 or 1,000 additional cores that we add on to Ethereum 1x so that we already get performance boost? Actually, I want to make an additional point because we have a bit of time, although I don't want to make it too long because otherwise we're here till 11. I think this analogy also really nicely illustrates sort of how the design philosophy is different. Like dApps for Ethereum 2.0 don't have to care about which shard they're executing on, which is somewhat similar to a multi-core processor. Whereas if you want to code for a GPU, you have to explicitly write your dApp for being able, or your program to be able to use the video card capabilities. And I think this is somewhat similar to what I'll explain here. If you want to write your dApp to use Mosaic as a dApp, you'll have to write additional contracts. But it might be worth for some use cases. And so my claim is, if Ethereum is the world's computer CPU, then Mosaic is a GPU you connect to accelerate your computations. And so what is a blockchain, right? Like a blockchain has 2 parts. It has a supply side and a demand side because it needs to be in economic equilibrium. The whole point is that no one is doing this for generosity. It's a for-profit motive to run a validator. So if it's not profitable, no one's going to keep running the chain. And so on the supply side, Mosaic is a dApp, a set of contracts on Ethereum 1x with an open set of validators, and you need to stake ETH and OST to finalize Metablock chains and get rewards from transaction fees in OST. On the demand side, any dApp developer can now deploy EVM contracts to one or more of these Metablock chains or cores. I'll get into that. And you can pass messages between the chains. So you can send both ERC20 tokens or other message data from Ethereum 1x to this core or back. And then within each core, now you can comfortably run at 300 transactions per second. Plus, and this will be the point, you don't have to pay for proof of work. And this is also where in 2015 this idea, well, for me, 2016, this idea really started. In 2015, there was a huge Bitcoin fork rerun or hard fork, and it was caused by what was later described by Jason Teutsch as, now the name slips me, but I'll just explain it. Sorry? Yeah, the verifier is dynamic. It's always good to have backup there. Namely that you need to be inefficient to make proof of work work. because proof of work only works if the amount of time you're spending on verifying the actual transactions is negligible compared to starting to finding the next nonce. And that was what happened in 2015, because a huge part of the mining pool effectively just said, like, you know what, if we skip these 200, 300 milliseconds of verifying the transactions, we have 200, 300 milliseconds ahead of everyone else of finding nonces. And so for a while they were successful, but eventually also they just started including bad transactions. And then later on someone noticed, and there had to be this huge reorg of Bitcoin. And so Deutsch, then still in academics, I think, and now Trubit, like analyzed this and sort of said there's this verifier's dilemma. Like proof of work only works if it's inefficient, because you need to be negligible on the useful amount of computation. But if we can build a POS system, a proof of stake system, on top of the proof of work that we're already expending, then we can use the same bits that we're already securing with proof of work to secure vastly more amount of work, and we want to reward that work with just transaction fees, not with a fee to produce new blocks and find a nonce, because that we know is inefficient. And so I briefly want to go over like how the contracts work. So these boxes are like representations of contracts on Ethereum. And so a validator joins a specific core, so one of them, by depositing both ETH and OST on Ethereum. And initially, this somewhat connects to the previous talk. So you need to earn reputation throughout your life as a validator, and the stake itself helps. Well, so I don't want to get into this now, but we can ask questions if you want. The reputation, in our case, is earned throughout this process, and it defines how much your reward is relative to the others. But every vote counts for one. So if you have a lot of money, you need to create a lot of validators. But we'll get to why it's still Byzantine fault tolerant and secure.
So, how is this different from Plasma?
So Plasma is based on fraud proofs, right? So you can only do certain stage transitions within Plasma, and then if any invalid transition would happen on the Plasma chain, now you need to report the fraud proof on Ethereum, and then people can exit, blah, blah, blah. Here, it's a traditional consensus engine. So I call this a Metablock and a Metablock chain, because the idea is really just re-implementing a consensus engine at layer 2. And so the finalization of a block is a Byzantine vote of the validators on Ethereum.
Okay, but I mean, as far as I know, you can also put like a POS or POA or what you want, like kind of algorithm on Plasma, I think.
Well, I would love to have this conversation, but I'm not aware of any. Well, I'm aware of some people working towards like full EVM capability on a Plasma chain, like LeapDAO and Sol EVM, and I'm very good friends with Johan. But I'm not aware of like them having a full EVM interface.
Yeah, I'm working with Leap, so let's talk later.
Okay, yeah.
Yes,
love
sorry.
to talk. Yeah. So I mean, yeah, absolutely, yeah.
I've been researching on the Casper, so Ethereum 2.0. FFG. So how is different between the amount of money depositing for Ethereum Mosaic 1.0 between the...
So, I mean, the reason I like the GPU analogy is because if you think of your old desktop, it's a card you plug into it. And so the same here, like it's a set of contracts we deploy and then build out a validator pool and a demand side for it. But anyone can take the same contracts and deploy them with their own rule. Like you can deploy multiple instances of this on Ethereum mainnet, no one's stopping you, right? So the rules of like how much is staked depend on the implementation. And specifically in our case, we are working on an algorithm for requiring that increasingly some percentage of the reward you earn you can take out, but some percentage decided by the governance is added to the stake so that the stake keeps increasing and we start out with, so that we can grow with demand, because otherwise...
So it's close to a POS, right? Then POW.
I will go through more details and maybe
Okay,
then it
yeah.
will become clear, because we actually
Yeah.
also rely on Casper FFG.
Okay.
So like in 2016, I built Ethereum plus Tendermint, and then I'm now sort of hopping using Casper FFG, which sort of took inspiration from that, and then using this at layer 2 to build this layer 2 consensus engine. So I'll talk about Casper in a second.
Thank you.
Okay, great. So next slide. So as soon as you sort of, if you join on Ethereum as a validator, there's a concept of Metablock opening, which I won't go into detail because I wanted to sort of paint the big picture, but just if you would take the quote like from the next Metablock, it has a specific meaning. Then the validator needs to join on this auxiliary system, and on this auxiliary system he needs to play Casper FFG. So why we want to do that is because we don't want to expend new proof of work or have other algorithms. We just want to have a way to finalize chain history based on any block proposer mechanism. With more detail, we actually play this twice. You need to play it once to observe the state of Ethereum 1x and agree on that, and once to finalize your own chain, so that you also have information being able to be transferred from Ethereum 1x onto the auxiliary system. But now, I don't know, do people want me to explain Casper FFG a bit, or yes? All right. So Casper FFG works by finalizing a history after it's been published, right? So with Tendermint, every block is only committed if it has a supermajority of 2 rounds from the validators. With Casper FFG, the original gadget was also to like take away the economic finality of proof of work. So we don't really care anymore about which blocks are produced. We still want to have some noise reduction, of course. But once the blocks exist, now we're going to cast specific vote messages that need to, and they're of the form where you identify a source and a target. And so as soon as, and then there's specific rules. So the construction is such that there's specific rules that you can prove certain properties of these checkpoints. And so specifically what you want is that there cannot be 2 contradicting histories of alive with more than a 2/3 majority. And so that is then proven to not be possible unless you would sign contradicting vote messages. And if those contradicting vote messages exist, they're very easy to verify. So we can easily slash you on Ethereum 1x immediately as soon as you try to finalize contradicting histories on the auxiliary system as well, because the vote messages themselves are very clean. And we know that if they exist, you're accountable for it as a validator. So if you see a history of supermajority vote messages finalizing a certain history, now you know that this history is finalized. I mean, it's a little bit more complicated than that, but that's sort of the basics. I hope I got that right. But what is really nice now is that we have a really good noise reduction mechanism, right? Because on this auxiliary system, the validators are playing Casper FFG to finalize a history, and now it takes a very specific form to bring back to Ethereum mainnet to say, like, you know what, this is our proposal of what has happened, and we propose that as a valid finalization of the auxiliary system. It's now a very condensed format And so we can present this to this core contract. And if it's indeed valid, like if it satisfies all the constraints of Casper FFG, now we know that at least these validators of this core have a supermajority for it. And if no one got slashed, there wasn't a contradicting history. But that's not enough, because we don't want to weaken our security. So imagine that you now don't have one core, but 1,000. You now need to divide your validators over those 1,000 cores. And then I get 1,000 times less stake representing any finalization. So we want to make sure that the total stake in this chip, I think of it as a chip now these days, but like in this DApp, is securing any of the cores. I've been neglecting this side of the room, I realize, sorry. And so that's why we introduce a committee, but in some sense you can think of it as a traditional blockchain system, right? Some leader needs to propose a block, and that is happening on the auxiliary system with the finalization of the sidechain. Any segment on the auxiliary system that is finalized is a valid proposal. You can now pre-commit this on the core contract with those validators to get it to be a valid proposal within the system. And now we want to make sure that we commit it. And so we only commit it, or how we commit it is by, in the near future, selecting a random committee from all validators that now need to do a couple of things. And so it's important that they're randomly selected from all, right? Because we want to have scalability. If we would just ask all million validators to validate this transition of one core, it wouldn't work. If we would rely just on the core validators, it would be weakened security. So we want to randomly reselect from all validators now to be in this committee contract to evaluate this block proposal. And in order to successfully do that, these committee members, they must be able to get the previous state of the core that was committed. So the previous commit, which might be like a day old, a week old, need to be able to get the snapshot of that state database. And then they need to be able to get all the transactions that are proposed state transition in this Metablock. And then what is important, they need to prove that they recomputed the full state transition. Because otherwise they would just be lazy and they would wait for someone to show up with the result. And now they would just like vote with whomever has done the work. So we need to make sure that in the committee contract, they also need to prove that they did the work. Namely, get the old state, recompute the state transition, and then show that proof that they did the work. And then it gets very interesting because the data availability problem is a really tough problem because it is subjective. Whether or not I get the data is a subjective question. I might just have a lagging internet connection, or the data might be being withheld from me. So it's very hard to quantify that. But here we try to make an approximation to that, because we're saying that this newly selected committee in the future has to be able to get the old data and recompute it. And so that's some approximation of the question, were they able to get the data, which is the data availability question. And so as a bit of context, the reason that the data availability problem is really hard is because Ethereum is, like we said, a Pentium 1 processor, so it can't do a lot. And if we would ask it to reevaluate all the data, we wouldn't get scalability. But if there would be a corrupt majority in the core, then they're obviously not going to present the bad data that they want to get committed. So you do need to address sort of an approximation of the data availability. And like I sort of said, with the committee formation that's randomly selected, we've evaluated, again, the whole stake that was present in the contract. And we can support up to 10 or 100,000 validators. Roughly, we aim to have like 100 per core. But of course, this depends on demand. If no one's using it, there's no transactions fees paying for validators, and it's not going to grow. And so a last point, and I'll get like back to higher level stuff, and if there's questions also. Of course, this wouldn't work if I need to wait for the finalization of Ethereum to finalize my auxiliary system before I know whether or not to send the bike. So it's very important, and that was a design principle from the start, that the two systems are asynchronously connected, so that there's no time constraint between the two. And so whether this process of committing to Ethereum takes a day or a week and happens once a day or once a week doesn't matter, because the auxiliary system keeps finalizing at normal Casper FFG speed its own history. And it knows that eventually, if it needs to, it eventually will be held responsible by a committee for any of the votes at any point. Those votes can be brought to the committee contract, and they will be held responsible. And then the last point, so we've established sort of an extension of Ethereum, and now we want to be able to transfer information between the two. So we have a concept of message boxes. There is an outbox and an inbox on both sides. But if you have an outbox on Ethereum 1x, you can put a message into that, and then every time information or consensus goes either way, now you can prove all the messages that are in the outbox and send them to and copy them in the inbox. And so that can be used for locking up tokens and re-minting them on the other side and redeeming and unstaking the same way, or any stateful information you can pass through to this message box. You can write your own for that matter. And so how do you build on top of this? So right now, we have Mosaic Zero. We didn't call it that, but now we call this Mosaic 1. So we call what we have so far Mosaic Zero. You can either work on the EVM interface, and then you definitely need to talk to us because it's still a bit rough. And all the code is in like GitHub OpenST, sorry. But like I said, we sort of wanted to make sure that there were real uses. So we've also further polished this for Web 2 applications. And if you go to platform.ost.com, it uses all the underlying architecture, and you just have to like click through web pages to use it. But it uses like a contract framework that we call OpenST. It has a non-custodial wallet for iOS and Android. And then we have built a relayer service, so meta transactions to contract wallets that you can implement in your own app to make transactions happen on Mosaic Zero right now. And also anything that's on Mosaic Zero will automatically move to Mosaic 1 when it launches. And then Mosaic 1 is what we're actively working on. You'll sort of notice that this is a little bit bare minimum, like my slides are black and white. And it's somewhat deliberate because as a company, we want to build the demand side. So we have this, if you go to platform.ost, it's all polished and documented, etc. And we think that's important to get like Web 2 applications on board. But that's on the demand side of the blockchain. We explicitly don't want to own the supply side, so the validator network. We want it to be an open validator set. We don't want to have our hands on it. Obviously, we'll run validators in it. But the whole point that this is sort of like done outside of the company is to never have owned this piece of code. And so it's definitely sort of why I keep presenting here. And so we're aiming to have a first version of that end of this year. And today I created a new Discord channel if you want to discuss, you can join there. And then, so for example, what have we already built? So we have one application that is on Ethereum mainnet with Mosaic Zero. And they're now rolling out to like beta users. So it's beta users of the application with real Ethereum tokens. And they had an internal point system that they called Hornet because the app was called Hornet. And the app is a gate dating app, by the way. So people using this app have absolutely no interest in Ethereum or cryptocurrencies. They're there to find guys. But they sort of have this internal community. So if you translate or report bugs or moderate, you earn points. And that's where we started. So we transformed those points internal to the app to LGBT tokens. And so right now it's a very limited use case, but it helps us stay within legal constraints, plus also test the technology. because the app itself has like 30 million downloads. We have 12,000 beta users, and we're slowly rolling it out. So in a week we have, well, it's a week and a half now, so we're at 700. We'll keep pushing that up to a few thousand. But this was the whole idea for us. This was like, let's make sure that Ethereum is used for real use cases. And that means that people who don't know about Ethereum can use it. And that means that it also needs to be really, really easy. So where we do put a lot of our company focus is making this UX really easy. And so what we developed, for example, is a smart contract wallet, non-custodial, that lives in your phone. But you can recover the PIN. If you lose all your devices, you can recover access to the contract in a non-custodial way with just 6-digit PIN. It takes 12 hours, so there's a delayed function on the contract, and it's a different talk. But it was very important for us that people who don't know about Ethereum don't have to go write down 12 words in order to use this, because then there will never be adoption of the technology. And so that's sort of as a little bit of a self-promotion here, the last slide. Thanks. Yeah, that's it.